We talked before about the gate level implementation of the design for the combinational logic. In this video, we'll talk about how to design more complex circuits using what's called the block level design method. In the block level design method, you have a bigger circuit, a complex circuit, and you want to use a smaller circuits to build this circuit. How do you do that? You start by decomposing the main problem to obtain formulas that govern the operation of this large circuit. Then identify the small repetitive units that you want to use, and then rely on the formulas that you obtained and start cascading the units together. Okay, this is the first example. Build a parallel adder. What is a parallel adder? It's a circuit that adds two 4-bit numbers together and a carry in to produce a 5-bit result. The circuit will look like this. This is the first 4-bit number. This is the second 4-bit number. And this is the carry in, which is a 1-bit. This circuit will add X and Y and C0 together. Of course, this will result in a sum of 5 bits. S as the sum of 4 bits and the final carry, which is C4. Okay, let's decompose the problem to obtain the formulas for the large circuit. The two numbers that we want to add, X and Y, can be added by adding these 3 bits together. The Cn, which is this one, the first bit of X, and the first bit of Y, to get a sum, S0. And the carry here will go to the next stage. Now, to do this addition of the 3 bits, we can use a full adder. On this full adder, we put the X0 and the Y0 and the Cn. The result here is S0 and C1. Now, the next thing to do is to add these 3 together. How do we do that? We can also use a full adder. In this full adder, we put X1 and Y1 as inputs. The other input we take from the carry out of the first full adder. So we can connect this C1 here to Cn. Now the result is S1 and a carry, which is C2, that is taken to the other stage here. So we connect C1 as an input to the second full adder. Now we can repeat this thing with this one here, which needs a full adder, and this one here, which needs a full adder. The result will be 4 full adders connected together in this fashion. This is the Cn, the first full adder with the inputs X0, Y0. Now the carry of this full adder is taken as an input to the second full adder, and the carry of the second full adder is taken as an input to the third full adder, and so on. Now this is the final carry C4, and this is the final result, a sum of 4 bits and a carry. If X was 0, 0, 1, 1, and Y had a value 0, 1, 1, 1, and we put the inputs here, and C0 was equal to 0, then the addition will be taken this way. This full adder will do this addition with this being 0, and this full adder will do this one, and this full adder will do this, and the last full adder will do this, and we will get at the output 0, 1, 0, 1, and the final carry of 0. Note that the carry propagated through the full adders, cascading full adders, and the carry propagated through the 4 full adders, from one full adder to the other full adder. Also note that the two inputs, the 4-bit X and 4-bit Y, are applied to the inputs. That's why it's called a parallel adder, because it adds all the bits together in parallel. This is called also a ripple carry adder because of the propagation of the carry from one full adder to the other. Let's do another example in using the block level design method to design a 4-bit incrementer. 4-bit incrementer. What is a 4-bit incrementer? It's a combinational device that has 4-bit input, and the output is S0 through S3 will be incremented by 1, and we have also a final carry because the output is 5 bits. So the input is 4 bits and the output is incremented by 1. Okay, if the input X had a value 0, 0, 1, 1, then the output S will have a value 0, 1, 0, 0 because the device added 1 to the input. How do we do that? You look here, we can say that we can use a half adder to do this part of the addition. If we look here, we can say that we use a half adder to do this. So we use the half adder repeatedly in the 4 stages here. This will result in a circuit that looks this way. The first half adder has an input which is Y, which is always equal to 1. This is 1. And the other input is X0, which is this one. Now we have a sum which is S0, okay? And the carry of this half adder is propagated to the second stage, to the second half adder here. Okay? And the input X1 is put as an input to the second half adder, and so on. So we get 4 half adders cascaded together to give me the 4-bit incrementer. We have talked about parallel adders. We call them ripple carry parallel adders because the carry passes through from the full adder to the other full adder and so on. Okay, now where does this problem come from? Let's assume that the full adder takes, for example, 10 milliseconds to stabilize its output, that is S0. That means C1 will come out after 10 milliseconds here. Now, this full adder will have to wait for the C before it stabilizes its output, S1, even though the inputs X and Y are available. That means S1 here will be stabilized after 20 milliseconds. Now this goes through, it propagates this delay to here through C2. So C2 will be stabilized as an input after 20 milliseconds. That means S2 here will stabilize after 30 milliseconds. And the final output, which is S0, S1, S2, and S3, will not be stabilized until 40 milliseconds has passed. Now, can we overcome this problem? Yes, if we redesign the parallel adder using a technique called look-ahead carry. Look-ahead carry means anticipating the carry before you have to wait for it to appear on the output. Anticipate its value. Okay, let's look at the full adder. This is the full adder number 0. It has the inputs X0, Y0, and C0. Now, let's assume that the output of this gate here is called P0. And the output of this gate here will be equal to P0 ANDed with C0. The input to this gate is the output of this gate. Let's call it G0. So in this case, S0 is the exclusive OR between P0 and C0, and C1, the carry, is equal to G0 ORed with P0, C0. That is what C1 is. G0 is equal to X0, Y0. And P0 is the exclusive OR of the X0 and Y0, and this is C0. From the very beginning, these values are given and known. In general, this is the full adder circuit in any stage. Si is equal to Pi exclusive OR with Ci. Ci plus 1 is equal to Gi ORed with Pi ANDed with Ci. We have seen this is C1. Now, let's look what C2 is. Can we anticipate what C2 is? C2 is replacing I here with 1. That means C2 is equal to G1 ORed with P1 ANDed with C1. And this is C1. C1 is equal to this expression. If we put this expression here. And now, so now we know C2. It's available before. We do not have to wait for the output C1 to come in order to find out what C2 is, because C2 is given in terms of X and Y and C0 in this equation here. And this is it. G1 ORed with P1, G0 ORed with P0, P1, C0. Now we can anticipate what C3, the carry of the third stage, what is it equal to? Replace I here with 2. So we get G2 ORed with P2, C2. And this is equal to this. Replace C2 from this equation here. Okay? And we get this. Notice that C3 here is known right from the very beginning, because G2 is known and the P values are all known. So I do not have to wait for C2 to come in to get C3. Now I can construct a circuit that will give me the carry C1 in terms of C0, G0, P0, which are X and Y and C0 from the very beginning. I can construct a circuit to give me C2 and construct a circuit to give me C3. I again do not have to wait for the propagation. These circuits are called carry look-ahead generators. This is a carry look-ahead generator for C1, a carry look-ahead generator for C2. This here is circuits that generates C3. These are the three circuits and their output. These are the inputs. Remember what G0 is. It's X0 ANDed with Y0, which are given immediately. Now this is the circuit for C2, and this is the circuit for C3. Now going back to the ripple parallel adder that we talked about that has the problem of the delay, if we disconnect these lines and connect here the generator for C1, the circuit that generates C1, and we connect here the circuit that generates C2, and we connect here the generator for C3, like so. This is the carry look-ahead generator. It generates C1, C2, C3, and we connect them in this fashion to the ripple carry parallel adder. This will result in a circuit called look-ahead carry 4-bit adder, because it adds 4 bits together. But there is this look-ahead for the carry at the final circuit for the new adder that resolved the problem of the delay. and this is called look-ahead parallel adder. Look here to see the look-ahead generator in between the inputs, the direct inputs X and Y, and here we name them A and B, and the output. Now let's build a subtractor. How do we subtract? We subtract two numbers, X and Y. X minus Y is the same as X plus minus Y. Notice that I say plus because we want to add and subtract here. It's not an or, it's a plus. Okay, minus Y in digital systems is represented as the 2's complement of Y, which is Y bar plus 1. So if we add X to the 2's complement of Y, we get X minus Y. Remember the parallel adder, whether it's a ripple carry or look-ahead carry. Okay, it adds the X number with the Y number. So what we have to do, we add the X number, which we put here, and now here we should put not Y, but the 2's complement of Y. The 2's complement of Y is the first complement plus 1. So if we put here the first complement of Y, which is this, and we put here a 1. So this adder will add the 2's complement of Y to X. So the result here, S, will be X minus 1. And this circuit will be a subtractor.